Okay, so first things first, I've prepared a tutorial sheet for you. First things first, let's get rid of that monitor thing. Preferences. So I've prepared a tutorial sheet for you and put it online where I've been storing the materials. If Chrome's going to wake up. We had that problem before, didn't we? Look at that crash dump. Yeah, that's not good, is it? Clearly I need a new laptop. Okay. So, lecture notes. That's obviously off my homepage. And then most of the lecture notes are up here. And then at the bottom you'll see tutorial 3. Okay? So that's targeting the sorts of well, that's useful, isn't it? So sort of questions, start with the univariate Gaussian, put a prior over it, do maximum likelihood solutions, move to the multivariate. You haven't actually done this this multivariate Gaussian fit, but you should be able to do it using these gradients that are given. Okay. So that's this. This is the solutions you're looking for: the mean and covariance of a multi-dimensional Gaussian. Then do the same thing, but a Bayesian treatment of the mean, not the covariance, just the mean. Okay. So this activity here is just completing the square, collecting the terms in mu, looking for the posterior, and then doing the same thing for the marginal likelihood. Sorry, let me just... okay, so if that's there, well, okay, right, so it's there, right. Then, regression with a basis function model. So we saw that last time. So this is the basis function. It could be any basis function. I'm just saying, for example, here's a basis function. And then they're giving you a vector of basis functions, and then a matrix of basis functions, and then the likelihood of an individual data, so single output, given the basis functions and some parameters. Maximum likelihood solution for those parameters. Yep, so we've been through that in lectures. Gaussian prior over that, so same sort of thing, just making you do the same thing again with different models. Look for the posterior for W, given this prior, and show that that's the covariance and that's the mean. That's basically the example we did in the lectures, but with basis functions instead of multivariate inputs. Look at these two things. Think about what happens when m is greater than n in the two different cases. So in this case and in this case, that's important. That relates to overdetermined and underdetermined systems that we talked about. And then finally show the marginal likelihood. So we're playing with that marginal likelihood, and here I've given you the matrix inversion lemma for helping you do that marginal likelihood. And then the final one, which I need to run through now actually, is principal component analysis. So you get a multivariate data set, P features and N data points. So that's that notation saying that it's N rows and P columns. And that we want to express that data with a low dimensional, it's got a mean and a low dimensional representation, which is mapped up through the vectors, and then we use this Gaussian prior over now the latent variables, not over the mapping matrix as we did for Bayesian regression. So then you need to write down the data likelihood, and then you need to combine the prior to show this, which is actually what we'll just go through now to start the lecture. So here we go, journal. So is that clear? Yeah. So that's the tutorial that's taking you through the sort of things that I'm expecting you to be able to do in case of examination. Okay? Yeah, just in case there's an exam at some point. So, you know, if you go through that and you feel comfortable with those materials, you're going to be in very good shape. Think about it, that's all the sort of thing we've done. Just play with those quadratic forms, understand prior likelihoods, how likelihoods are formed, what the relationship between an error function and a likelihood is, yeah? We just keep doing the same thing again and again. But the nice thing about the thing we're doing, I mean, while we're doing the same thing again and again, it's very useful across a wide range of systems, and we're seeing that by, well, I hope that story will become even clearer in Friday's lecture, when we actually start to show you some of the results you can get, more complex things with what appear to be fairly, maybe less interesting linear models. Okay. So, in that tutorial sheet and also last time, we've got this, this form here. This is the likelihood of one element from a matrix T. So we've got this matrix T, which is T1, 1 to sort of T 1p, and then Tn1. Oh, someone pointed out last time, yeah, and I'm doing it again. I'm changing between big N's and small n's for number of data. Sorry if I do that. I can't actually remember which I specified in the notes. But big N and small n just means the same thing. So just a matrix filled with these elements here. That's our data. And we're saying one element of this matrix is given by this likelihood here, where this likelihood has a Gaussian form. And we're also using a mean, which I should have put on this side, apologies. Mu j squared. Sorry, now I've left off the latent variables. Minus wj comma colon transpose x I comma colon. Okay, so just for a refresher, that matrix X is these latent variables. They're in the same form as this T. So you've got x11 to sort of x1q. So X is q-dimensional. And then we have down to xn1, xnq. So that's our matrix X. And then also, so this is one row. So that corresponds, that's a column vector which is extracted from one row of this matrix. Yeah? And then we've got W, which has got P rows. So let's just put these things in here. N, P, Q, Q. It's got P rows, and there's a W11 to W1Q, and a W P1, W, PQ. Those are the elements in there. Yeah, all filled up. And this guy here is a vector. Again, always column vectors. Even though it's extracted from a row of the matrix W, it's a column vector. So we can recover any element of this matrix. So what this is saying is that this element of this matrix here, T11, is approximated by a mean value, mu j, which is constant, which is for that column, yeah? So each column has its own mean. Mean value, but then, I mean, and let's ignore the mean for the moment, so just ignore the mean. What it's then saying is that this guy is given by the inner product of this vector and this vector. Okay, plus some noise.
The inner product of what?
This vector wj, colon, and this vector xi, colon. So one of these vectors and one of these vectors. So t11 would be this vector and this vector. t12 would be this vector and this vector below.
I think we can't see
Yeah,
your
we can't see your
pointer.
mouth.
Oh, sorry, yeah. Bugger. Okay. Well, one thing I can do. You'll be able to see it on the video later. Maybe. Now I'm wired up, so I can't move. It's all going to go wrong. Okay, I'm going to unplug myself. Well, I can, but I'll have to keep changing between it and what I'm writing. Whoa. About what? Can you see it now? Okay, I'll put the hand on. Oh, you will. We'll see how it goes like that. Okay. Sorry. Between, you see when you said this vector and this vector, so you couldn't see anything. Okay. This vector and this vector do t11. So the first row of here, notice they're q-dimensional, right? So these match up in dimension across here. I'm starting to use my fingers on the thing here. You definitely can't see that. This dimension across this way matches with this dimension across this way. So this element of the matrix here is being given by the inner product of this vector and this vector, yeah?
Our estimate of it.
The estimate, yeah. That plus some Gaussian noise. Yeah. Now then this guy here, the next row, the second row on here, we need the n, because it's going down this way, is the second row here times that one there. So to get the second row and the first element, it's that one times the top one. But to get the second element, it would be that one times the second one. So you get that? So in what actually is saying, I mean, in matrix form, what this is saying is that T is approximately equal to, let's get the dimensions right, big X times W transpose. We can see the dimensions are right here. Remember this trick, important trick here. So N by Q is this matrix here. W transpose, because it's flipped around, is Q by P. So those guys cancel, that gives us an N by P matrix, and what we're saying is the elements of that matrix are made up by this low rank thing. If we set Q equal to P, then you could get this, in fact even if you set Q to P minus 1, you can get this exactly. This will become an equality if you set that. But if Q is less than P, you can't represent exactly all the elements in this matrix. So you're trying to represent them up to some Gaussian noise. Now, that's one way of looking at it. Yeah? So we've got this matrix factorization, and that's a way of looking at it that was used in, say, the Netflix challenge to do. People use exactly that representation as part of their algorithm to win $1 million in this thing called the Netflix challenge. Okay, so PCA is related to that. I can't write challenge, but there you go. Can you see that now? Oh, no, you can, yeah. Okay, good. Okay, that's better. But that's really not the interpretation I sort of sold you last week. That's another interpretation. The interpretation I sold you last week was that you've got some vector x, which is like an input to a regression. Yeah, so this is like an input to a regression, and then we multiply that by a weight vector w, which is just like a regression vector that we were learning about last week, and that is approximately equal to our data point Tij. And then, okay, but no one gave us the inputs. So we're going to deal with the inputs as nuisance variables and integrate them out. So we're going to try and infer what those inputs are. So that's an alternative interpretation, and that's the one that Hotelling put on it. Now I can't spell Hotelling. Okay, I'm going to spell it messily. So I know it ends in an ing. I think there's two L's. Okay. So what we want to do is deal with the x by integrating it out. So we need to have a probability of xij, which is Gaussian. And we're not going to put any variance. It's unit variance, so no variance parameter. And that was the mistake last time, because for some bizarre reason I decided to go off and integrate a w, which is regression. Okay. Oh. So, let's try and get rid of some of the rubbish I've pulled down. So this is our likelihood. Okay. This is our likelihood, and that's our prior distribution. So x is appearing in here. But what do we need to do? We need to, this is the likelihood for one element of the entire data matrix. So we're going to make an IID assumption, which stands for, anyone? Independent, which means we can do what? Multiply the distributions, and identically distributed. So each one has the same distribution. So our noise is IID. So what we then write is the probability of t. Now, the entire data point t, so all of j, so that's my colon notation I use there, given w. So now all of w is involved because we need all j of w's, but we only need one of the x's. Okay, and that's going to be the product of all these guys. So the product of these guys means that at the front we get to the power of p, which was the dimension of our data coming out here. So that becomes 1 over 2 pi. I mean, you've seen this before. So p over 2, yeah? You've seen that several times before. And then the product in the exponential means a sum. Okay, so the sum of j equals 1 to p of tij minus mu j minus wj colon transpose xi colon squared all over 2 sigma squared. So that's our likelihood for the ith data point. And then we can write down our prior for the ith data point in the same way, but this is q-dimensional now, not p-dimensional, because it's the latent variables. So independence again across those latent variables. There's variance of 1 we're using, and I'll explain that at some point. Okay, and then this thing here, sum of rj equals 1 to q xij squared. Can anyone tell me, what can I replace, well, what do I want to replace the sum of xij squared with, which gives me vector notation? How can I write that in vector notation, anyone? Very good. So that term there, as has been pointed out, is xi colon transpose xi colon. Yeah, because that's just, the inner product is the multiplication of each of those elements summed all up, which is the square of each element summed up. Okay? Now, slightly less obviously, there's some equivalent thing going on here, the sum of a bunch of elements squared up. But we need to write down a vector in j. So here it's obvious what the vector in j is, it's xij, but basically this term here, that'll be back in a sec, we need to transform into, if we want the vector, then it's going to be ti colon minus the vector mu, all elements of mu. Now the last one's a little bit tougher. We want the vector j, so that vector in J is actually recovered by by multiplying W, the whole matrix W, times X. Now then your question is, oh, is it W transpose X or is it W X? How do we know the answer? Dimensions, precisely. So if we look back at our dimensions, in order to multiply this matrix W times a row of this X, we have to have P by Q by Q by 1. Yeah? So any row here becomes a column vector, so it's Q by 1, and this is P by Q times Q by 1. So basically, we need a W X I colon. So that is the vector underlying that. So of course, we can write down that this term itself is given by okay, I hope you guys see, it's nice for me because I can always move my maths to the left. But you guys thought, oh, he doesn't need much space there, so minus X I colon. So this is just the vector form of that bit there, yeah? And we need that. We need always in vector form to do our integral nicely. Everyone follow that? Okay, so what do we do now if we want to find the posterior? So the posterior for xi, given the data point w sigma squared and mu is equal to what? And the other question we might ask is the marginal likelihood of the ith data point, which is not dependent on x anymore because x is gone. It's that, yeah? So those are the two things that we're interested in. And how do we get those things? Anyone? We've got the prior over the x. We've got the likelihood over x. How are we going to do it? Oh, well, we've done this 8 times now. Bayes, well, yes, but implicitly we are going to use Bayes' theorem, but we're going to do it by this sneaky trick that we've used several times before. In shorthand notation, so dropping the subscripts and the other conditioning here, all that conditioning is on both sides. P of t given x times P of x is equal to P of t given P of x given t. Yeah? This is Bayes' theorem because you just need to pop that on that side. You see in the yellow there, yeah? To get Bayes' theorem, you just bring that on that side. But it's even more obvious than Bayes' theorem because it's just the product rule matching the joint distribution. On both sides, it's P of t, comma x, P of t, comma x, yeah? Both that's what this equality is saying. So you're given this, and you want this. And the way we're doing it, the way we've been doing all these, is just to multiply those guys out. And in the Gaussian case, that means summing in the exponent. Yeah? Multiplication of 2 exponents. The only term, because the terms we're interested in are only appearing in the exponent, we could ignore the rest. Because both of these are probability distributions, and they must be normalized. And what we're going to do is this is Gaussian times Gaussian. So what's this side going to be? Gaussian, yeah, Gaussian times Gaussian. Must be Gaussian times Gaussian. Everything's Gaussian. So we have to recognize, we have to extract the component of that Gaussian, which is the posterior, and the exponent of that, the component of that Gaussian, which is the marginal. And this is. Yeah, then we'd be doing another course. No. Yeah, if they weren't both Gaussian, so there are examples. So for example, if you wanted to deal with this variance, you would have to have an inverse gamma. And what you would find is you have an inverse gamma times a Gaussian, and then on the other side you would have a gamma times a distribution which is sort of called a student t. So it's not quite as nice. Gaussians are really elegant in this sense. Yeah, that's why That's why they're widely used. They're very, very tractable because you're always staying within this space of everything being Gaussian. It's very, very unusual. I mean, it's a good question because this isn't the typical form. But the fact that this happens is why it becomes very powerful that we can do a lot of extended things. You're just having massive Gaussian distributions over everything you're interested in, which means specifying these correlations. Okay, so how does that look? So looking at the exponent, this first term of the exponent here, and I'm going to multiply that out as I go. So I'm taking this, so we're needing to get the two of these terms from the exponent together. I'll take just this, so there's a factor of minus half sigma squared in front of this as well. Let's put that in. 1 over 2 sigma squared, let's not make that ambiguous. So I'm going to multiply these guys out. Starting with t, which is a vector because it's all features from the ith data point. That's what my colon notation is noting, yeah, that it's the ith row. Next bit, right. Sorry, let me do that bit again. I was too fast for myself. Let's view this as t minus mu. Sorry about that. I want to keep the t and the mu together. So it's t minus, and let me do this in yellow down here. Make it clear that it's part of the main derivation. So that's minus a half sigma squared of t, the ith row of the matrix T, minus the mean vector, transpose, same thing again. And then again up on this side, we'll view that as one vector. So the next term we'll write down is the cross term. So let me think about which way I want to write this. I'm going to write this as plus 1 over sigma squared, because remember it appears twice. So it's the standard, the cross term, it's appearing once and it appears in sort of transpose form, but the transpose is equal to the same thing. So I'm going to write, again, ti. So this is the term from this term multiplied by this term plus this term multiplied by this term, yeah? So that's why the sign's changed, because it's positive. Okay? Now then, minus the quadratic term coming from these guys, which is 1 over 2 sigma squared minus 1 over 2 sigma squared x okay, and then we're missing one thing, which is what? What have we missed out so far? Anyone? P of x, yeah, the prior. Thank you. So the prior is in vector form, very simple, minus 1 over 2 x I colon transpose x I colon. So what's the next stage? Now we've written that out. What do I want to do now? That's the exponent of this guy, and it's the exponent of this guy, because they're equal. What am I interested in finding here? Probability distribution in which variable? Yeah. What did I start with here was a probability distribution in t. Now that I've blown it apart, a t given x. But I want to actually get I want this guy to not be dependent on x, whereas this guy was dependent on x. So what I'm going to do first is extract all the terms in x. Yeah? And by extracting all the terms in x, I know this guy shouldn't be dependent on x. I have what should be the posterior distribution. So the next stage, because the prior was over x and we're looking for the posterior over x, it's extract the terms in x. So which terms in x am I looking for? What's the quadratic term? Anyone tell me what the covariance is going to be for x? You should be able to look and see that immediately now. So which terms are the quadratic? Is this term quadratic in x? Anyone? No. Is this term quadratic in x? Last two. So what's the trick? How do I combine these terms together? What do I need to do to what's in the middle here? I've done this like 3 times. Yep. Very good. So let's keep the factor of 2 out the front. But that's exactly right. Okay, that's the quadratic term. That goes down to there. So what's the covariance of the posterior? You now can see that immediately. What's the covariance? In a Gaussian form, what does the covariance look like? It's the inverse of that, absolutely. So now you have, so you really need to all get familiar with this. So if I'm going to call that Cx, the covariance, then we now know that Cx is equal to W transpose W over sigma squared plus I inverted. Yeah? So how are we going to get this linear term? The linear term is going to come, remember, from trying to fit this whole thing into the form, I'm just writing the x now, but the posterior mean, which I'll denote by mu x, c minus 1x, x minus mu x. Yeah, that's the form we're trying to get these x bits in. There's no x in there, so we're ignoring that for the moment. So we've got this. That's the covariance. But if we multiply out this one, then we recover that in x, the linear term in x is of the form mu x transpose, let's put the factor of half in here, mu x transpose c x minus 1 times x. So we can match this x up to there, that x there. That's all right. So we know that mu x transpose c to the minus 1 is equal to this guy. Yeah? What do we do now to deal with the cx on that side? The inverse cx? How are we going to deal with that? How can I get rid of that? Come on, people. Does it make it easier if I say, make it scalar? How do I get rid of the c on, so how do I get rid of the c on the left-hand side and bring it to the right? Multiply both sides by c, and of course in the matrix case, what's the right thing to do? Multiply by cx. So of course that means that mu x transpose, well, I'll just okay, let me write that out so that I'm not skipping a step. Ti colon minus mu transpose w cx, which means if I transpose a vector or a matrix, I have to transpose everything and reverse the order of multiplication. So I basically need to go, which is cx transpose, which cx is symmetric because it's a covariance, W transpose, because W is transposed, and then this thing is also transposed, so it's just a vector. No, CX transpose, but it's symmetric, CX. So CX, because it's a covariance matrix. Yep. Okay, so pulling down our covariance, we can also write that fully out. Oh, and what have I very naughtily missed? Anyone tell me?
1 over sigma.
Perfect. 1 over sigma squared. I've been... Okay. So, pulling down this term and writing it out like this, we've got that mu x is W transpose W over sigma squared plus I minus 1. 1 over sigma squared times the whole thing. Ti colon minus mu. Now, one thing I really want you to notice now, this is not, okay, so let's not get confused. This is the mean of the posterior. So this is like posterior over W. So one thing I want you to notice about this mean and covariance is it's virtually bang on the same as the regression mean and covariance. Only everywhere we used to write x, we now write W. So this is the mean of x, not the mean of W. So everywhere we used to write x, we're now writing W. But it's the same derivation. Yeah? It's just the multivariate one, so there's a multivariate output. So that makes it slightly more complicated. But this posterior mean is the same derivation as we've had before. The only difference is that everywhere we had t before, we're subtracting a mean off it. Yeah? And then where we had w before, x before, we're putting w, and where we had w before, we're putting x. Why does that happen? It happens because of maths. But specifically, look at how these little boys are appearing together here. Always appearing as an inner product. Doesn't matter whether you put the Gaussian over one or the other, the same thing drops out. You know, if I now told you, oh, actually, change mind, guys, we'll make x our regression weights and w our regression input, okay? This derivation follows through exactly, and you just have to substitute w's for x's and everything appears out. So you just have to remember, in PCA you're integrating out x, which is what I failed to do last time, thank you. And in linear regression you're integrating out Bayesian regression, you're integrating out w. But the derivation's the same, and the principles underlying it of collecting the quadratic terms are the same. Okay, but what do I have to do now? Because now I've done a very nice job. What did I do here? Or what did we do here? Collected the quadratic term. We've dealt with that term. That term has now been taken away to happy posterior land. This linear term we've also dealt with. It's in happy posterior land. But what did we do when we dealt with that linear term? What did we generate? If we multiply, we matched it up to this form here. But this form here also has what in it? So this x, c minus 1x, matches to these guys. Mu c minus 1x twice matches to those guys. What are we left with? Come on, there's one other term there. What would it be? Yeah, mu x transpose c minus 1 mu x. So we generated one of those in order to write it in this form. So implicitly in our posterior there's one of those flying around. So what do we have to do? It's a negative one of those, so we have to add it back in. In order for these two to match up, we've effectively generated this term. Yeah? So because in order to cancel it, we sort of this is what's been going on. We've got rid of that as well. But that didn't exist. But maths is magical, and we could just pull it out of thin air as long as we subtracted it off. Yeah? So now we're left with these two terms. What are these two terms? What are they associated with? We've extracted the posterior. We've got the mean and covariance. All we're doing is recognizing this quadratic form is that of a Gaussian in X, and these terms do not have X in them. So we've extracted what? P of X given T. So what are we left with? P of T. So we're left dealing with P of T, which is the marginal, which is the other component we need. Let's just copy that. And then we need to add to that. Let me save this. I forgot to save last time's one. Sorry about that. Unless, of course, no, I think I did forget to save them. But they're on the video. The videos are online. So we now also have to deal with this term, which is arising because of extracting the posterior. But it's not dependent on X, because neither mu, because this is the posterior over X, so neither the mean or the covariance of that posterior are going to depend on X. Sorry, that's CX. Okay, so let's write that out in full. That's a plus half. Now, what was mu x? It's got a ti, comma colon minus mu, and in transpose that's going to appear first. And then it's got this, let's look at it in terms of Cx, because we're going to lose the Cx here. We're going to lose one Cx, right? So it's got a sigma to the squared, and it's got a W, and then it's times Cx, yeah? So but that Cx times this Cx minus 1 just gives us no Cx, and now we can start with the next, with the final mu x. So that bit there is that. Let's do that in orange. So that first bit there is that, and now we need the mu x, and I'll just take this one because I don't want it in terms of Cx, I want to see everything. So this mu x has got a sigma squared. I'll keep that back for the moment. Goes W over sigma squared plus I minus 1 W transpose Ti colon minus mu. I've not done that very tidily. Sorry. Ti colon minus mu. So that's that term. Move the bottom of my arrow back. Oh, and I'm missing the sigma squared. I said I was going to save that, so let's put that. Let's put that in. Times 1 over sigma squared at the end. I could put sigma to the 4 there, but I just wanted to keep that like that, yeah? Okay, and then this other term here is this Ti colon minus mu transpose Ti colon minus mu minus a half sigma squared. So that's what we've got. Now, does anyone remember how we're going to deal with this ugly looking beast? Pardon? There is a formula, precisely. So again, we want to break out okay, what's immediately obvious actually is that we've got, okay, there's a secret I hiding in here, as we all know, but he's actually I sigma minus 2. And then if I'm going to write half that now I'm going to start the matrix. So I'm going to extract out the matrix from this side too. So, because it's minus half of that, this one is now minus. So I sigma to the minus 2 times W times W transpose W, or let's write Wi sigma to the minus 2 W plus I W transpose I sigma to the minus 2. So I'm writing that in matrix form because I want to match it up to the matrix inversion lemma, which would be given. I'm not expecting you to remember this. You'll see in the tutorial it's given. And the matrix inversion lemma says A minus 1. I'm doing the matrix inversion lemma the long way round to do this. So that's D A minus 1 B plus C minus 1 D A minus 1 is equal to A plus B C D minus 1. So on that matchup, A is equal to sigma squared I, B is equal to W, D is equal to W transpose, and C is equal to I. So that gives us the marginal likelihood has this covariance. Call it CT, because it's the covariance over T, is therefore equal to A is sigma squared I plus B is W plus C is I plus D is W transpose. So the covariance, okay, so this is inverted in here. So because it's inverted, what's inside is the covariance. So the covariance is equal to that. Now what does that smell like? That smells exactly like our covariance for the marginal likelihood of linear regression, but we just had an alpha there because we put a variance over the alpha prior. Now I said I'd explain why you don't need that in this case. And the reason you don't need that is because you're going to fit W. If you did have the alpha, all that would happen it would appear here. Yeah? But that's just scaling W. So it's not identifiable. You know, you could make alpha 5 million, and then W would just be W divided by 5 million square rooted. Yeah? So it doesn't matter whether you put it in or not. It would just pop out here and just scale W, which is another set of parameters. So we typically ignore it. So that, defining that, so we basically got all that rubbish there into this CT to the minus 1 form. And so we see we've got it in a form Ti, comma colon, minus mu, transpose sigma squared I plus alpha W, W transpose minus 1 Ti, comma colon, minus mu. That's our quadratic form. So it's a Gaussian with a mean mu and a covariance given by that. Now it doesn't matter what, you'll see this in the tutorial 3. Doesn't matter what this form is, if you want the maximum likelihood solution for mu, so this is now a marginal likelihood over the data, so we need to find the other parameters. If we were to do that by maximum likelihood, you'll do this in the tutorial, you'll always recover regardless of what the covariance is. Yeah, the mean vector is equal to the mean of the data. The more complex object is this covariance, which has this special form that I'm going to talk about at the beginning of next time. So the other thing you need to fit, the other things you need to fit are these two, sigma squared and W. I don't want to talk about the maximum likelihood solution for them because it involves a reasonable amount of manipulation. In fact, oddly, it wasn't discovered for 62 years. So people didn't know there was a nice maximum likelihood form for this for 62 years. And I'm kind of quite proud of the fact that the people who discovered it were Tipping and Bishop. And Mike Tipping is my sort of close friend and was a colleague when I was at Aston, and Chris Bishop was my PhD supervisor. So 62 years it discovered them, so I'm not going to make you reproduce the proof of what they are, but they turn out to be a fairly simple thing, which is the eigenvalue, well, they related to the eigenvalue decomposition of the covariance matrix. So the first half of next time, I'm going to talk a bit about the eigenvalue decomposition of that covariance, and then I'll just start showing you the sort of research type of stuff. So it's not something I'm going to want you to be able to derive, but it's going to be something I want you to know is you'll have to learn that what these maximum likelihood solutions are. And that is known as principal component analysis, the eigenvalue decomposition of the covariance matrix. But it has this lovely interpretation here as this particular type of Gaussian model. The other thing I want you to notice here is that this matrix is P by P, because it's P by Q times Q by P. But it's rank Q. What does the rank mean? Yes, the number of eigenvalues which are non-zero. That means it's not invertible on its own. But by adding this diagonal term, it makes it invertible. This, if you were to do it the other way around, if P was larger than Q, sorry, if P was smaller than Q, this matrix here wouldn't be invertible, W transpose W. This is important because it's actually, actually is regularized by I. But in the regression cases, these matrices appear, right? So when we're doing maximum likelihood for regression, you looked at matrices like X transpose X. And you had to invert that to do the maximum likelihood solution. In fact, that's written in the tutorial. But if the dimension of X, or phi, the number of basis functions, is larger than the number of data points, that's not invertible. And you can only do the Bayesian solution. You can't actually recover the maximum likelihood solution. And that's an important point that comes out in the tutorial. So please start working at the tutorial this week, and then maybe you can ask me questions about it next time. Okay, we've got to finish because those guys were waiting outside last time, and I don't want to upset them again.